Hello, everyone. Today we're going to be talking about titrations and acid and base neutralizations. So, titrations are a very common laboratory method that's used to determine the concentration of an unknown acid or an unknown base using a neutralization reaction. This is what we'll be using it for. However, titrations can be used for redox reactions and various other needs in the lab. So, when we are performing a titration, we always have two different substances. We have what we call a standard solution. So that is a solution of known concentration. So in order for us to find, say, the concentration of an unknown acid, we need a standard solution of base, or base that we know the concentration of. And vice versa, if we were trying to find the concentration of an unknown base, we would need a standard solution of acid in order to find the concentration of that base. So we call this standard solution the titrant. We also have the solution with unknown concentration, that's what we're trying to find, and we call this the analyte. So we've seen acid-base neutralization reactions before. They have this basic setup to them, right? We have an acid, it's reacting with the base, it gives us water and salt. An example, we have hydrochloric acid plus sodium hydroxide, that's our base, producing H2O and sodium chloride. Again, this is a double replacement reaction. So the sodium and the chloride come together, the hydrogen and the hydroxide come together and give us two new products from our reactants. So again, if we had, say, an unknown concentration of hydrochloric acid, we would need to have a titrant that is sodium hydroxide in order to figure out what that unknown concentration is. Again, the known concentration solution is our titrant, and our unknown concentration is our analyte. So, to perform a titration, we have this new laboratory tool here called a burette. We have not used this before, but it's composed of just two main parts. We have this really long, narrow glass tube that has these graduations, we call them, the markings, to help us measure the volume. And towards the bottom, we have a valve, also known as a stopcock. And when it is horizontal, when the handle's horizontal like it is in this image, the valve is closed. When it is vertical, up and down, the valve is open and the liquid can flow from our burette down through the nozzle down here. At the very top of our burette, you have an opening as well that allows us to fill it with titrant. So here's another slightly more in-depth image, right? We have our ring stand, which we've used before. We have these specialized clamps that we use called burette clamps, and they're designed specifically to hold nice and stable our burette. We have our burette here with our stopcock or nozzle at the bottom. We have an Erlenmeyer flask that we use to hold our analyte and to catch the titrant as we release it. So that's what we have at the bottom. The reason we have an Erlenmeyer flask, not a beaker or something else, is because it allows us to swirl it around and allow it to mix really easily without us risking spills. So again, we fill up our burette with the titrant. You can use a funnel up at the top. And before we run any of our titrations, it's important that we take our initial reading of where the titrant level is. That way we can take our final reading after we perform the titration. And then we can just subtract the two in order to figure out how much titrant we use, because you need to know the volume of your titrant used in order to figure out the concentration of your analyte. So I mentioned that they have graduations or markings on the burette. One important thing, one difference though between this and a graduated cylinder is that you'll see that the smaller number is on top. That's abnormal if it weren't for what we were using the burette for. So again, our initial reading is going to be higher up. We're going to have more liquid in our burette than our final reading where we have released or used up some of that liquid. So in order to keep the numbers positive when we take the difference, it's important that we have the smaller numbers up top and the larger numbers at the bottom. So reading a burette is very similar to reading a graduated cylinder. We have these markings. We have a 3 here and a 4 here. We have 10 marks in between, or 9 marks, meaning that each one is 1/10 of a milliliter. But we also have to remember that we need to estimate 1 digit past the smallest marking, right? Think back to the very beginning of the year. So here, for our initial reading, we would have 3 milliliters and 4 milliliters. We measure at the bottom of our meniscus, and we would see that the bottom of the meniscus is right there at 3.123, 3.3 milliliters. But since it's right there, perfectly even with it, we would have to estimate 0 at the end. So our initial reading would be 3.30 milliliters in our burette. After we've run our tests, we've used up some of it, our volume inside the burette has gone down, right? Because we've used up this amount of our titrant. We would take our final reading down here. This is 3.1, 3.2, 3.3, 3.4, 5, 6, 7, 8, 9. This one's also perfectly even with it. So it would be 3.90 milliliters. So to figure out how much we used, the titrant used, we take the final reading, so 3.9 milliliters, and subtract our initial reading, 3.30 milliliters, and that will give you the amount of the titrant used. So plug that into your calculator, or do it in your head if you can. So if we do 3.9 minus 3.30, we end up with 0.60 milliliters. And remember, we're subtracting, so the number of decimal places needs to be the same as the least, which is 2 decimal places. So we'd record it as 0.60 mils. So here we have some quick practice. We have burettes labeled A, B, C, D, and E. We'll do A together and then give you a moment to do some on your own. So to read burettes, you need to see the marking above and below where our meniscus is. So we have 6 and 7. So our reading is going to be somewhere between 6 and 7. We have 9 markings here, just like before, right? So we would have 6.1, 6.2, 6.3. Our meniscus, the very bottom, remember that's where we read it, is between 6.2 and 6.3. So we would estimate this last digit is 6.2 something. To me, this looks right in the middle, so I could say 6.25 milliliters being my reading. So I gave you the answer for B. We'll do that one together too. We have 35 through 36. We have 35.5, 0.6, 0.7, 0.8. This is again, looks right in the middle between 35.8 and 35.9. So I would say that's 35.85 milliliters. So take a second and do some, or C, D, and E on your own, and we'll talk through it in a moment. Okay, so for C, we're between 7 and 8. This would be 7.1, 2, 3, 4. Looks like it's right on the 7.4 mark. So in that case, 7.40 would be a perfectly accurate reading. For D, we have 45 and 46. This is between 45.1, 2, 3, 4, so 45.4 and 45.5. Again, all these seem to be either right on or right in the middle. So 45.45 would be a great reading here. If you're, a couple digits off or a couple values off in our last digit, that's totally fine. If you think it's 45.47 in your reading, that's okay. The last digit is an estimate. Just do your best to be consistent. Then our last one, we're between 5 and 6. We have 5.5, 5.6. It seems to be right on 5.6 right there. So 5.60 would be a perfectly acceptable answer. All right, so Next new term is what we call the equivalence point. So we are going to be adding titrant to our analyte until we reach what we call the equivalence point. That equivalence point is the point at which the titrant has completely neutralized our analyte. So we're going to be adding it very slowly, very carefully until we've completely neutralized our analyte, or what's in our Erlenmeyer flask. And again, for acid-base reactions, we have the amount of hydrogen ion is equal to the amount of our hydroxide ion. That's how we know that we've completely neutralized our unknown. So a titration curve looks something like this. You'll see that as you add more and more of your titrant, the pH doesn't change very much until all of a sudden it jumps up really, really quickly, right? This is our pH on the y-axis and the amount of sodium hydroxide, or our titrant in this case, for this titration. So we need to be really, really careful because, again, pH is a logarithmic scale. It increases by a factor of 10. So it doesn't seem like anything's happening, but then it jumps up super quick to a really high pH and then stabilizes again. Our equivalence point is right here in the middle. So especially once we start getting close, we need to be very, very careful if we want to reach an accurate equivalence point. The indicator we use in these reactions between a strong base and a strong acid is phenolphthalein, because it gives us a nice bright pink color as soon as it turns basic. Here's a picture of what an ideal endpoint should look like. So if we do it perfectly, which it takes a lot of practice, you'll get this really nice light shade of pink here. But as soon as you overshoot it, which can be as little as one extra drop, it turns this really dark pink, right? If we go back to this image, right here is as soon as it starts to turn pink on our indicator range for phenolphthalein. But if you do just a little bit more, it shoots up, right? This is just a little bit more volume of sodium hydroxide and turns this really vibrant pink, and that's how you know you've overshot your endpoint, which is what you're trying not to do. So I saw this and thought it was funny. If you guys got the chance to do this in real life, hopefully later if we get the chance or in college, you'll see that just one more drop can be enough to accidentally overshoot the endpoint. You can even ask the people, the students from last year's chem class, and they'll verify this for you. So indicators, like we saw the other day, there's lots of different indicators, right? Indicators are chosen such that they change color at the range of pH that we want. So for us, we're just going to be using strong acids and strong bases. So phenolphthalein is perfect for our needs because we are testing two solutions that give us a neutral endpoint. However, the solution itself at the endpoint may be basic if we have a strong base and a weak acid. It can be neutral if we have a strong acid and a strong base. This is what we're going to be working with for the most part in this class. And it can be acidic if we have a strong acid and a weak base. So given different tools that we are titrating with and different chemicals that we're titrating with, we need to use different indicators that are around the endpoints that we know we're going to have. So to solve titration problems, there's two different methods. There's stoichiometry, which you can use for pretty much anything if you're creative enough. And there is our number of hydrogen, molarity of acid, volume of acid equals number of hydroxide, molarity of base, volume of base, neutralization reaction that we've used previously. And this works well for strong acid, strong base reactions, which, like I said, is all we're going to be worrying about in this class. So to keep things simple, we're just going to use this reaction here. So we can do an example. If we have 20 milliliters of strontium hydroxide and it is neutralized after 25 milliliters of standard 0.05 molar hydrochloric acid is added, what is the concentration of strontium hydroxide? So our balanced equation would look like this, right? We have hydrochloric acid, strontium hydroxide produces water and strontium chloride. Since strontium hydroxide is 2 hydroxides per each molecule, and hydrochloric acid is a monoprotic acid, we need 2 hydrochloric acids for every 1 strontium hydroxide here. It's important to keep our charges in mind. So again, we just use this equation here. So take a second, try and plug in each of these 6 variables, or see which ones we have and which ones we don't. So the number of hydrogens in our acid, we would look at our acid here. Hydrochloric acid has 1 acidic hydrogen because we have 1 hydrogen up front, so we could have a 1 in that spot. The molarity of our acid, they tell us it is a 0.05 molar hydrochloric acid solution. That would be our molarity. The volume, they tell us we have 25 milliliters of this acid solution, so that would go here. So we have all 3 components of our acid, or of the left-hand side of this equation. On the right, we have number of hydroxide ion, we have molarity of our base and volume of our base. So if we look for number of hydroxide ion, strontium hydroxide has 2 hydroxide ions here, so we'd plug in a 2 into this variable. The molarity of our base is what we're trying to find, right? The question says, what is the concentration of strontium hydroxide? So Mb is our variable here. And then Vb, the volume of our base, they tell us we have 20.0 milliliters of strontium hydroxide, so that would go in for Vb. So we do 1 times 0.05 times 25 milliliters equals 2 times the molarity of our base times 20 milliliters. To get Mb by itself, we can just divide both sides by 2 and 20 milliliters. We end up, once we plug into our calculators, getting an answer of 0.03 molar as the molarity of our base. So again, these calculations are just the same as what we've been doing the last couple days. However, we know how we get this data once we run our calculations.